My name is Fernanda Sobral, and today I'm going to talk about chapter 18 of this book, Physics for Engineering, which is called Heat and the First Law of Thermodynamics. So I'm going to explain the general principles of this chapter and the most important formulas we will use. So first, it is important to know what is heat. That is our first point. So heat takes place when energy is transferred between a system and its surroundings or from one object to another due to a change in temperature. So we can have a positive and a negative heat. When the heat is going into the system, we're going to take this as a positive heat, and when the heat is going out of the system, we're going to take it as a negative heat. So, what is like the mechanical equivalent of heat? What do I mean by this? It's the units by which we measure heat. So we can use both calories, and a calorie is defined as the heat needed to raise the temperature of water by 1 degree, of 1 gram of water by 1 degree centigrade. And we can also use BTU, which is the one for the English system of measurements, which is the heat needed to raise the temperature of 1 pound of water by 1 degree Fahrenheit. So these calories can be transformed to joules, and 1 calorie equals 4.186 joules, and 1 BTU equals 1055 joules. So this is like the way we measure heat. Okay, so we can also see a relationship between heat and work, and this relationship can be obtained through the following integral. So we have heat,
and it can show the different ways whenever work is positive.
So this integral
to a final point. So for example,
when we solve it, it of course equals work, and it can also be seen as the integral from the initial to the final volume of the pressure in terms of the volume. So from this we can obtain something called a pressure volume diagram. So a pressure volume diagram is what it says, right? It plots pressure against volume, and it can show the different ways whenever work is positive to go from an initial to a final point. So for example, we can have these
diagrams in order to understand how to get from one point to another.
So we have pressure here and volume here. We can have an initial point here and a final point here. So to get here we can go maybe in a straight line or in a curve, maybe like this, changing volume different. For example, in this case, we have a constant pressure for a while volume changes, which could mean, for example, a change in temperature, and then we decrease only the pressure as volume stays the same. So whenever work is positive, we can use these diagrams in order to understand how to get from one point to another. So in this case, we can have both open paths and closed paths. An open path is, for example, like this. It goes from an initial to a final point, and they are completely different. And a closed path is, for example, like this. You have this point, and you go through different changes in pressure and volume, but you end up in the same point, which means that the initial point equals the final point. So, well, that's a relationship we can find between heat and work. So, the next bit of theory we want to understand is the first law of thermodynamics.
So from this law, we can know that the
basic principle
must
always of this law is that energy must be conserved. As we know, energy cannot be destroyed. It stays the same in the universe. It tends to go from an object to the universe, but it can also be the other way. And it has to be conserved between the
final energy minus the initial
energy in the system and the surroundings. The total has to be always the same. So from this, we can know that the difference in energy must always equal.
So for example, when there is no work made, we will have that the heat will always equal 0. So
initial energy,
because the heat belongs to the system, so there will not
which
be
is
an
here
exchange.
by in we mean of the system, of the interior of the system,
If
minus
our system are, for example, two objects, how
no,
the
the
transfer
final
of
energy
heat
minus the initial energy. And this can also be represented as the heat minus the work. So this is a very important formula that can be applied for a variety of problems whenever we're dealing with changes in energy. So for example, when there is no work made, we will have that the heat will always equal 0. So because the heat belongs to the system. So there will not be any exchange, so maybe we can use this in order to understand how, if our system are, for example, two objects, how the transfer of heat takes place in those two objects. So from this, we can apply this first law of thermodynamics to a variety of processes. And we can have, for example, adiabatic processes.
First law of
diabatic, in which heat does not flow. So in our equation, we can lose the heat part, and we only know that the difference in the internal energy should equal work. We can also have isochoric processes, which are of constant volume. And as we saw before, this volume and the pressure have a relationship with both heat and work, which are the variables for our first law of thermodynamics equation.
There is no difference in
and whenever we have
energy. So
a constant volume, the initial point equals the initial volume equals the final volume. So therefore, there is no work made.
We can also have something
And we only have this.
I'm sorry.
Then we can also have processes with a closed path.
We can also have
Which
something
is
that
like
is called
before is
free expansion process,
the initial
in which
point
the volume
is
is not
equal to the final point.
which means that we
And
go,
in this case, there is no difference in
I don't know.
internal energy. So this will be equal
Because
to
the volume
0,
changes.
and if we
So
solve
in
for
this
the
case,
heat,
the
we will
difference
have that the heat equals the work. We can also have something that is called
I'm sorry. We can apply the first law of thermodynamics too.
sorry. We can also have something that is called free expansion processes, in which the volume is not constant, which means that we go from an object, I don't know, supposing this is an sphere, this is small, to an object this big, because the volume changes. So in this case, the difference in energy,
Variable for heat minus should equal
and
0.
the definition of work,
Which equals the
So-
pressure.
another type of process that we can apply the
Pressure will
first law of
change,
thermodynamics
will
to
change.
is an isobaric process, in which pressure is a constant.
Sorry,
So
as the
constant P.
pressure stays equal. So another way we can have it is through a constant
In an
temperature.
isobaric process, the change
And in this case, what is important
in the
are
internal energy
graphs
equals Q,
called
which is
isotherms
the
that
variable for heat, minus
show
the definition of work,
we can
which
go from one
equals
to
the
another
pressure,
whenever the temperature is constant.
because in
So
this
we can have
case,
something like this.
pressure will stay the same, but the volume
When we
will
join
change
the
with those changes in pressure.
Pressure, volume,
And
temperature.
sorry,
So those are like the different applications we
as
can
the
have.
pressure stays equal.
The-
So another way we can have it is through a constant temperature.
for the first law of
And
thermodynamics.
in this case, what is important
So
are
then we
these
also
graphs
have,
called
an
isotherms
important
that
value,
show
in
the
this
way
case, which is a specific
we
heat.
can go from one point to another one whenever the temperature is constant. So we can have something like this maybe, or something like that, when we join the relationship between pressure,
What is heat
volume,
capacity
and temperature.
from
So those are like the different applications we can have for
obtain
the
heat, and it is defined as the
for
amount
the first law of thermodynamics.
temperature of an
So
object
then
by
we
1
also
degree
have
centigrade. And
an
it
important
equals the
value
following equation. The heat
in this case, which is a
equals
specific
the
heat.
heat capacity times the difference in temperature. And of course, this should
So
be
first,
energy,
in this case, we have
units
two
of energy
different
divided by units of
values.
temperature.
One
Which
is
is
heat
divided by
capacity,
units
from
by
which we will later
And from this, we can
obtain
the specific heat.
the specific heat, and it is defined as the amount of energy needed to raise the temperature of an object by 1 degree centigrade. And it works in the following equation: the heat equals the heat capacity times the difference in temperature.